Okay, so let us solve the last two exercise problems. The first of which is exercise 13. We have already come across the same problem at the end of that section involving integers in this book, which is a special case of the Chinese remainder theorem. We have already solved this, but now we are again going to solve this using the pigeonhole principle. So it goes like this. Using the pigeonhole principle, prove that if m and n are two relatively prime integers and a and b are any integers, then there exists an integer x such that x is congruent to a mod m and x is congruent to b mod n. Okay, now there is a thing to note about this exercise. The relation congruence modulo n, the way we have defined it, a is congruent to b mod n, this relation between a and b. The modulus is a positive integer. Here, however, that condition is not imposed on m and n because they are moduli in these two relations. But the only thing that is given is that they have to be relatively prime. As such, none of them is equal to 0, but they may be negative. So we actually have to think of this relation in this extended fashion, where our modulus is no longer positive. It of course is not 0, that is meaningless, but it can be negative also. However, the meaning is same. This just means that n divides a minus b. So with this small observation, we now start the solution. We have to prove that there is a simultaneous solution x to this system of two linear congruences. And there is a hint. Herstein has said how we are supposed to approach the problem using the pigeonhole principle. And he asks us to consider some remainders. Consider the remainders of a plus m, a plus 2m, etc. a plus mod n minus 1 times m on division by n. That is, if we divide these integers by n, we will get some remainders. Those remainders we are being asked to consider to solve the problem. So we accordingly start the solution. Let R0, R1 mod n minus 1. Note that this makes sense, this number. And this number is a non-negative number. Why? Because n is non-zero. So mod n is a positive integer. So that's why mod n minus 1 is a non-negative integer. Let this be the remainders of a plus m, a plus 2m, etc. a plus mod n minus 1 times m on division by n respectively. What it means is just that if we divide a by n, the remainder is r naught. Dividing a plus m by n, we get the remainder r1 and so on. Okay. Now, assume Ri is equal to Rj for some I and j satisfying these inequalities. Okay, we can assume without loss of generality that one of these two labels is larger than or equal to the other one. Okay. Now, if this is my assumption, if I have assumed that two such remainders are equal, turn out to be equal, then what is the consequence? Then n divides a plus jm minus a plus I n, which is nothing but j minus I times m. Why does n divide this difference? N divides this difference because you see, Ri is the remainder when we divide a plus im by n. Rj is the remainder on division of a plus jm by n. So that means a plus jm is congruent to Rj mod n and a plus im is congruent to Ri mod n. If we take their difference, a plus jm minus a plus in, this will be congruent to Rj minus Ri, which is equal to 0, congruent to 0, same. I mean, at least in this case. So this is equal, or let me write equal to 0, it's stronger. This is equal to 0 mod n. And that's why n divides this difference. Okay, so n divides this difference, and this difference turns out to be equal to j minus I times n. Now we invoke the hypothesis that m and n are relatively prime. Since m and n are relatively prime, recall that this means the GCD of m and n according to Herstein's notation. Since m and n have no factor in common, and n divides this product by a previous result, n has to divide j minus I. We must have n divides j minus I. Now look at these inequalities. J and I are integers and j is greater than or equal to I. So that means j minus I is non-negative. But at the same time, j minus I is obviously less than or equal to j because I is non-negative. And as such, it is less than or equal to mod n minus 1 or strictly less than mod n. So the only possibility is that j minus I has to be equal to 0 because that is the only multiple between this and its negative. Okay. This is possible only when j minus I is equal to 0 or j is equal to I. So our assumption that Ri is equal to Rj has led to the conclusion that the labels themselves are equal. That means if any two of these remainders are equal, then they are the same thing. Okay, two differently labeled remainders are not equal. That means these are all distinct. Hence, These are all distinct. How many remainders are there? Mod n, starting from 0 to mod n minus 1. And how many remainders do we get when we divide something by n? Same, mod n. So, by the pigeonhole principle, they account for all the remainders these are the remainders on division by n. When we divide by n, these are the possible remainders, and these are nothing but these in some order. Okay, so Rp is equal to 0, because 0 is appearing here in this list, and this list is nothing but this list in some order. 0 will appear here also somewhere. That means some Rp has to be equal to 0. For some P lying in this range. Hence, now Rp is 0 means what? When we divide the number a plus pm by n, then the remainder is 0. That means it divides that number. Hence, n divides a plus pm. So this is one conclusion we have got. Similarly, by considering the remainders of something else, now we consider these numbers b plus n, b plus 2n up to b plus mod m minus 1 times n, remainders of these on division by n, we obtain m divides a plus qn for some integer q lying between 0 and mod m minus 1. Now take x to be this integer, the sum of these two integers. Oh, this is not a, sorry, this is b. A plus pn plus b plus qn. One can see that for this x we have x is congruent to a mod m and x is congruent to b mod n. Let us see how that is the case. When we are dividing x by m, this contributes 0 remainder because it's a multiple of m. And note that m divides b plus qn, so this part also contributes 0 remainder. The only thing left is a, so x is congruent to a mod n. When we are dividing x by n, this part, this qn contributes 0. A plus pm also contributes 0 because that is divisible by n. So the only thing left is b. So x is congruent to b mod n. So that's how we get the solution to this problem. Okay. Now the last one. using the pigeonhole principle. Let me refill, okay. So this second problem, the last one, asks us to show that the decimal expansion of a rational number is repeating after some stage. That's what the problem is. Using the pigeonhole principle, prove what is the exact statement of the problem. Prove that the decimal expansion of a rational number must after some point become repeating. Instead of writing a general solution, what we will do is that we will consider some examples and see what is going on in those examples. That will tell us what goes on in the general case. So some people may object to it being an actual solution, but you will see that this is much more illuminating than a general solution. So I insist that this is a solution. Okay, a question arises at this point. If I can get by with just examples, what was the need for considering general solutions in the previous problems? The thing is that if you are considering examples to to say something about the general situation, your example or list of examples should exhaust all the possibilities. That should be carefully noted. Otherwise, you may inadvertently leave something out, not to your knowledge, and thereby the solution that you will get will be incomplete. Okay, but in this case, we will carefully cover all the situations, and we will see that although we are going to discuss just some numerical examples, we have to take the general fact out of that discussion. Okay, so we start with our first example. Let's find or let's determine the decimal expansion of this number 132 by 7. Okay, now if we want to find the decimal expansion of this, if we are just simply asked find the decimal expansion of this, most of us will start doing the division, the rule for finding decimal expansion that we have already learned in school. We are also going to do that here, but not in that fashion. What we will do is that we will again and again use the Euclidean algorithm to come up with the decimal expansion, and that will be much more clear than the other method that we have learned in school without understanding why it works. Okay, now applying the Euclidean algorithm, so we are saying this because we are required to say what we are doing. We get 132 is equal to 18 times 7 plus 6, where 6 is the remainder because it satisfies these inequalities. So 132 by 7 becomes 18 times 7 plus 6 divided by 7, and this becomes 18 plus 6 by 7. Okay. Again do it. And hold on. Let me write one more step. 18 plus 1 by 10 times 60 by 7. 6 is smaller than 7. To make it larger, we are multiplying and dividing by 10. Again applying the Euclidean algorithm. We get, now we are dividing 60 by 7. So now the remainder is 4. So 132 by 7 is equal to 18 plus 1 by 10 times 60 by 7. Now 60 by 7 becomes 8 times 7 plus 4 divided by 7, and this gives us 18 plus 8 by 10 plus 1 by 10 times 4 by 7. Okay, note that we have already applied the Euclidean algorithm twice to obtain the remainders 6 and 4. Okay. Since the possible remainders on division by 7 are these: 0, 1, 2, 3, 4, 5, 6. Continuing the above computation will lead to a repetition of remainders at some stage. So here what we are saying is that every time we are applying the Euclidean algorithm, we are getting a remainder. Since the divisor 7 is fixed and these are the possible remainders, these 7 numbers. So continuing this computation again and again, at one stage we are bound to have a remainder that has appeared before, a repetition. Okay. Continuing our computation for a few more steps, we get. So if we keep on doing like this, then we will ultimately get to something that looks like this. 132 divided by 7 is equal to 18 plus 6 by 7. The remainders that we obtain in this process, they are going to be put within brackets, within parentheses, to emphasize the fact that they are remainders. Okay, then after that we get 18 plus 8 by 10 plus 1 by 10 times 4 by 7. The second remainder is 4. These two things we have already obtained, but now new remainders will come after that. 4 by 7. So then this is equal to 18 plus 8 by 10 plus 5 by 10 square plus 1 by 10 square times 5 by 7. So 5 is the third remainder. Then this is equal to 18 plus 8 by 10 plus 5 by 10 square plus 7 by 10 cube plus 1 by 10 cube times 1 by 7. 1 is the fourth remainder. Then 18 plus 8 by 10 plus 5 by 10 square plus 7 by 10 cube plus 1 by 10 to the power 4 plus 1 by 10 to the power 4 times 3 by 7. 3 is the fifth remainder, and one more step. Times 4 by 10 to the power 5 plus 1 by 10 to the power 5 times 2 by 7. 2 is the sixth remainder. So note the remainders that we have obtained: 6, 4, 5, 1, 3, 2. Note that already obtained the 6 remainders. 6, 4, 5, 1, 3, 2. The only remainder that has not appeared so far is 0, which may or may not appear in the next step. If it appears in the next step, then we will have all the remainders with us. I mean, they have appeared. After that, the step after the next step, we are bound to get a repetition because everything that is available has already come. So something more that is going to be repeated from one of these. Or we may have a repetition in the next step itself. That happens when 0 does not appear. Okay, so we are bound to get a repetition in the next 2 steps. Computing one more step, we have this. One 32 by 7 equals 18 plus 8 by 10, 57142. Okay, so you see that after this stage, again 6 is appearing. So instead, we have not got 0. We have a repetition here itself. So in this step itself, we have the remainder 6 again. Okay, now we make the important observation. The important observation here is this. 6 by 7. Recall that we had 132 by 7 is equal to 18 plus 6 by 7. Then we did our calculation with 6 by 7. So if we write the expression for 6 by 7 from all these things, then we get something like this. 8 by 10 plus 5 by 10 square plus 7142. Have we not got 3? 8571. Okay, fine. 85 7 1 4 2. Look at this equation. Here we have an expression for 6 by 7 in a particular manner where we have negative powers of 10, in which again 6 by 7 is appearing. And this expression actually tells us the digits that are going to appear after the decimal point. Because when we wrote 132 by 7, that is 18 plus this.